Alright, let's take a look at the extraction of iron using the blast furnace method. So on Earth we find iron in the form of an iron oxide, Fe2O3. And this is found within a huge rock called an iron ore. And it contains lots of things, not just iron oxide, but it also contains impurities. Impurities such as sand, which is commonly known as silicon dioxide. So when we extract iron, we just want the pure iron. We don't want the oxygen, and we don't want impurities like sand. So this blast furnace method is basically just a method to get rid of the impurities, leaving us with just pure iron. And a byproduct of that also, which is slag, which is also useful and can be sold for profit. And we'll look at all that in this video. Now this blast furnace concept, it really confused me when I first learned it. It took me a couple of hours to learn this actually. But eventually, it's pretty understandable once you understand the concept essentially. Just don't memorize it. Once you understand what's actually happening and the reason behind for these things, you'll probably understand it. So I found this nice graphic online to help with that. So, also, you might have previously learned about something called the reduction with carbon method. Reduction with carbon. And that's essentially when you use a displacement reaction. So you might have a metal oxide, and you react that with carbon. And that's when the carbon steals the oxygen away, so it becomes carbon oxide with just metal. But this sort of thing only works in science labs or on really small scales. It's too costly to do on an industrial level. So this blast furnace method, this is used on an industrial scale in like huge factories where you need huge quantities of iron. And this entire blast furnace, therefore, is roughly 30 meters tall. It's pretty big. It's not just some scientific lab thing. It's a huge process that's used in factories all over the world. So let's look at the raw materials that we input. Now, we call these raw materials the charge. It's called the charge. And the charge essentially refers to all the raw materials that we enter. So we put in the iron ore in the form of hematite. Hematite is just the name of the iron ore that we're putting in. So hematite. We also put in some coke. Coke is just basically a fancy scientific term for pure carbon. So hematite is Fe2O3, iron oxide, and pure carbon is just carbon. And we also put limestone. Limestone, which has the formula of, what is the formula of limestone? CaCO3, calcium carbonate. Calcium carbonate is limestone, and some other metal scraps, but we don't need to know that for your GCSEs. You only need to know iron, coke, and limestone. Remember, coke is just pure carbon, limestone, calcium carbonate, and iron ore, the form of, we put hematite in, and it's called Fe2O3. And all of these combined together, the raw materials that we put in, they're called a charge. Okay, you might be wondering why we're putting the limestone in. What's that going to do with anything? Pure carbon, maybe we have something to do with carbon, something with hematite, because obviously we need the iron. But why limestone? Well, as aforementioned, hematite, it contains impurities, right? Such as sand. Well, the calcium carbonate basically removes the impurities. And we'll look at that in just a moment when we look at the equations and why they happen. So the raw materials get put in, like this diagram shows. They're dumped in and into the furnace. Now this reaction that occurs within the furnace with all these charges, it produces hot waste gases in the form of carbon dioxide. This is why this isn't, like, we don't see blast furnaces located within cities. They're located in, like, way out on the outskirts, near factories and in the industrial areas. It's also a form of global warming gas. It's greenhouse gas, carbon dioxide, right? So it produces waste gases. And we also input hot air. And we'll look at that in just a second. And this also produces two useful products. Number one being, obviously, the iron. And number two, we also produce something called slag. We'll look at both of these in just a second, but to briefly summarize, iron can go to make steel alloys, which then goes to make something like car body frames, refrigerators, basically anything. Almost everything is made of iron, and which then steel is just an alloy of iron, which is a stronger version. Remember, alloys are just metals combined with other metals or non-metals to make them stronger. And slag is basically just another byproduct of the iron extraction using a blast furnace, but it can go to make roads. So it can make roads, and it can also be used as fertilizer. It's a bit surprising, right? So roads and fertilizer. Let's look at the steps in more detail. Here's a more simplified diagram. We have our charge. Charge is entering from the top, and our iron ore in the form of hematite, carbon in the form of coke, and limestone, Fe2O3. Sorry, not limestone. Iron ore is Fe2O3. Limestone is calcium carbonate. Waste gases of carbon dioxide, hot air. This should say hot air. Hot air is inputted, and we have our iron and slag. So let's look at the process. Step 1. The oxygen, obviously oxygen is everywhere, so we don't include it in the charge that's being put in. The oxygen reacts with the coke. Now the coke is the fuel, it's what powers everything essentially. The oxygen reacts with the coke, forming carbon dioxide. So what just happened? Well, oxygen within here, obviously, we don't insert the oxygen, it's just there. And the coke has been put in, right? They're going to react together, forming carbon dioxide, one of our byproduct waste gases. So, and this also releases heat, immense amounts of heat. And that's why the temperature down here in zone 1 is around 1500 degrees Celsius. Not only is the hot air heating this area up, but obviously hot air isn't going to be 1500 degrees Celsius, right? When the hot oxygen in the air reacts with the coke, the carbon, it forms carbon dioxide, right? The coke is the fuel. And so when it meets with the hot oxygen, it's going to like combust essentially. And it's going to create immense heats, extreme heats, 1500 degrees. And as you go up and up in the surface, it starts to get cooler. It doesn't get hotter, it gets cooler. Think of it like this. The bottom is the hottest area, so as you get further away from the hot area, it's going to get cooler and cooler. So the top of zone 1 might be around 850 degrees Celsius, and then it might be 700 degrees Celsius. And near the top, it might be around 250 degrees Celsius. So just know that it gets cooler, and the bottom area is the hottest, 1500 degrees, because the oxygen reacts with the fuel of coke, forming carbon dioxide and also releasing heat at the same time, therefore making it super hot. Now let's write the equations in a slightly different color. The oxygen, remember oxygen is a diatomic molecule, it always exists in pairs, reacts with the coke. We said coke is just pure carbon, right? So just C. And that's going to create our product of carbon dioxide. Pretty easy up to now, right? One of the easiest equations. As you go on, it's going to get tougher, but so far so easy. So far so good, right? Oxygen reacts with carbon to make carbon dioxide. Now this carbon dioxide is really important. So that first of all, this process heats the area up, which is also important, but it also creates carbon dioxide, which is really important for our second step. So let's look at step 2. If I can write it. Step 2, the carbon dioxide that's just been formed, right? Carbon dioxide formed reacts with, what does it react with? It reacts with more coke to form carbon monoxide, forming carbon monoxide. Now these names can get really confusing. Carbon dioxide or carbon monoxide, what's the difference between the two? You've probably heard of something called a monologue. That's when a speech is given by one person, a monologue. Or maybe in English you've done something called monosyllables? Monosyllables. Yeah, monosyllables, just monosyllables. You probably heard of either one of these two things at least. Mono just basically means one. So when carbon dioxide was 2, di means 2. So dioxide means 2 oxygens. Monoxide means 1 oxygen. So it's just going to be having the formula CO. 1 oxygen, monoxide, monoxide, 1 oxygen. That's where the name comes from. And that's a pretty easy way to remember it. Dioxide is 2, monoxide is just 1. It's going to form carbon monoxide. What would the equation look like? First, oh yeah, I forgot to mention. O2 is obviously going to be a gas. Carbon is obviously going to be a solid. And carbon dioxide is obviously going to be a gas. What does this look like? Carbon dioxide is obviously a gas. It's going to react with the coke, the carbon, the pure carbon, right? And obviously that's going to be a solid. Did I write solid on the previous page? Yeah, I did. Yeah. So carbon is a solid. And that's going to go to form, remember, monoxide. So just 1 oxygen. So just 1 oxygen, carbon monoxide. And that's going to be a gas, just like carbon dioxide. we need to balance our equation. Balancing equation is just really simple. Just make sure you have the same number of elements on either side of the equation. You have 2 oxygens here, but 1 oxygen here. It's going to become a 2. 2 carbons here and 2 carbons here. So now our equation is balanced. So carbon dioxide form, it's going to react now with coke again, forming carbon monoxide. Now this monoxide is really important because it's very useful for a third step, and you'll see it all kind of links together, ties in together really well. Our third step, the carbon monoxide, is basically the reducing agent. I'll explain what this word means in just a second. Let's highlight it in orange because it's a key word. It's the reducing agent. And it reduces, so the iron oxide is reduced to just pure iron. Now, what does a reducing agent mean? Well, you can kind of imagine it from this. Iron oxide was Fe2O3, right? But it's been reduced into just pure iron. And obviously something else is going to be formed as well. This part just can't disappear. What do you think is happening? Well, the oxygen disappeared. So reducing agent is basically just, it's removing oxygen from any other substance. Reducing agent just means removing oxygen. Because remember, we had reduction and oxidation reactions, right? Watch my video on that if you don't know. Reduction is when you remove oxygen. So when the oxygen is being removed, iron oxide is reduced, so the oxygen is being removed to just pure iron. And a reducing agent is just what facilitates, what causes that process to happen. So iron oxide is reduced to iron. Let's look at the equation for that. Carbon monoxide was CO, right? That's obviously going to be a gas. And it's going to react with our iron oxide, which is obviously a solid because it's found in the iron ore. And that's going to go to form, what's it going to form? It's going to form pure iron, right? So that's obviously just going to be iron. And it's also going to, iron's going to be a solid, obviously. Let me just write that again. Fe. And iron is going to be a solid. And it's also going to form the oxygen. Well, if we have pure oxygen, we're going to have oxygen and carbon remaining, right? So it's going to form carbon monoxide, the gas, as well. And oxygen is a diatomic molecule, right? So it's going to be, let me write that again. CO2 gas. I'm kind of running out of space. We obviously need to balance our equation. Carbon dioxide, right? That's going to be our waste product. Essentially, we have 1 iron here and 2 irons here. So we need to put a 2 in front of here to ensure that there's equal numbers of iron on both sides. 2 oxygens here, but 3 oxygens here. That doesn't really add up. But we have 1 carbon here and 1 carbon here. So we just need these oxygens to balance out. We have 4 oxygens in total on this side, but we have just 2 oxygens on this side. So what if we multiply this side by 2? That's going to make the oxygens balance out, but now there's 2 carbons here, but just 1 carbon on this side. Well, that's not really going to work out exactly well, right? What if we raise this to a 2? 2 carbon, 2 carbon, 2 oxygen, but that's going to make 5 oxygens. What if you raise this to 3? 3 oxygens plus 3 oxygens, that's going to give us 6 oxygens. 2 times 2 is 4 oxygen plus 2 carbons. I think if we put this as 3, that'll fix everything, right? 3 carbons and 6 oxygens. How many oxygens do we have here? 6 oxygens, 3 times 3, so 3 carbons. Now it's balanced out. So this balanced equation process, there's nothing hard to it. Just make sure that there's equal numbers of each atom on both sides. That's the equation balanced. So essentially, we've had our carbon monoxide react with our iron oxide, creating pure iron, and our carbon dioxide, the waste product. Now this is in the form of molten iron. Now what happens to this molten iron is it gets cooled rapidly, and it's going to be, basically, it's going to create the product of iron. And we have one last step. We said that the, what was the term? I just forgot what, hematite. Hematite, which is the type of iron ore that we use, it's going to contain a bunch of calcium carbonate, which is basically, sorry, not calcium carbonate, that's just iron, Si2O3. This formula can get a bit confusing, but once you get used to it, you'll be fine. And this silicon dioxide is basically just sand. We want to get rid of this silicon dioxide. That should be a 2, sorry. Silicon dioxide is sand. Now the iron ores contain silicon dioxide and we want to get rid of it. What does this is limestone. That's why we use limestone. And silicon dioxide. And we want to get rid of the impurities, which is the sand in this. So the extreme heat, we have something called a decomposition reaction. Decomposition reaction. In biology, you probably learned something called decompose, when things break down. Decomposition reactions in chemistry is basically when things break down due to heat. So our limestone, Ca, let me write the formula in blue again. CaCO3 solid, because it's a limestone. The limestone solid is going to decompose due to the extreme heat. It's going to break it down. It's going to break it down into calcium oxide. Sorry, calcium oxide, yeah. CaO. And that's going to be a solid. And also carbon dioxide. You'll notice a bunch of greenhouse gases are produced. It's always carbon dioxide or carbon monoxide. But this bit is what's really important to us. When the calcium carbonate, the limestone decomposes, it creates CaO, right? The calcium oxide, and that's just carbon dioxide, but the calcium oxide essentially, it can react with our silicon dioxide in the sand. So CaO reacts with our silicon dioxide. They're both solids, by the way. They both react to get rid of the impurities, creating a very complex formula, CaSiO3 liquid. And this is what we commonly call slag. And that is calcium silicate. We call this calcium silicate. Okay? Let's just run through what just happened. The iron ore contains impurities like sand, because it's a rock, it's going to have a bunch of sand. Sand can be removed using limestone. Limestone, because it's in extreme heat, it's in the extreme heat of this furnace, right? 1500 degrees, 850 degrees, it's going to thermally decompose. When it thermally decomposes, the limestone becomes calcium oxide and carbon dioxide, our waste product. The calcium oxide reacts with the silicon dioxide in sand. The formula for sand is silicon dioxide. Two solids react together, forming calcium silicate, a liquid. That's called slag. Now, why is this important? Well, if we go back to our diagram here, we can tap off. I don't think this diagram is really good. Yeah, let's just use here. We can tap off iron, and we can also tap off slag. So this iron has been removed of its impurities like sand because of the limestone. It's removed the impurities. But slag, the product formed when the calcium oxide is reacting with the silicon oxide, that's the product formed. It's the product formed with the limestone that's used to be within the iron. So it's basically limestone plus carbon. And limestone was Si dioxide, and carbon is CO. Sorry, not CO, C. Yeah, limestone plus carbon. And that's why our final equation for that, if I can find the slide, calcium SiO3. All of them have reacted together to form slag. So what is slag used for, and what is iron used for? Iron can be used, it's an important component for when you make steel alloys. So when we have iron produced from blast furnaces, they're really weak. Iron, we don't use it most because it rusts really easily. It's really weak. So we create steel alloys. And with that, you can make stainless steel that's used in sinks and water bottles. It's a much stronger and anti-resistant form of steel. So essentially, we're going to turn that into steel alloys. And alloys, remember, it's just when metals and some other elements combine together to form a stronger version of that. And slag can go to form fertilizer to help plant growth. And it can also go to build roads, road construction. Pretty weird combo, but that's what happens. So slag and iron is the product, and slag you could say is the byproduct of when we're producing iron, because iron is the main purpose, right? And in all this, waste gases of carbon dioxide is produced, and a greenhouse gas, obviously, so it's located far away from cities because people don't want these huge factories within them. So yeah, that's pretty much it. You need to know all these equations, and once you kind of understand what's happening, it's pretty easy to understand. I hope this helped. Thank you for watching.